For assignment number 12, we're going to be doing an introduction to circles. And so for this warm-up, it's really investigating or understanding the different parts of a circle, like what is the center, what's the radius, what's a chord, what's a diameter. So in this first part, it just gives you a definition of a circle. It says it's a set of points in a plane that are equidistant, meaning the same distance from a point called the center. And the distance from a point on the circle to the center is the radius. So a circle is always named by its center. In this scenario of the Ferris wheel, the center would be P. So it would be called circle P. So for part A, it says name the circle. So if I look at all the choices of the points here, I need to pick the one in the very center. So that would be O. So this would be called circle O. Part B says for each of the points above, tell whether the point is on the circle, at the center, or inside. So let's label the ones that are on the circle. I'm going to label this first. So on the circle, at the center, and then inside. All right. On the circle, A, B, C, and D would be on the circle. So A, B, C, and D. At the very center is O. And lastly, the point that's inside would be point E. So use a straight edge to draw OB. So we're connecting from the center to a point on the circle. Where the endpoint's located in respect. So center, which was point O, and on the circle. So again, what we just created is the radius of the circle. And it says, how many times can you do this? How many radii, which is plural for radius, how many radii can you create? Well, I could create technically infinite many, keep drawing from the center to the point on the circle. So you could do that an infinite many times. Part D, use a straight edge to draw segment AC. So here's AC. Then use a straight edge to draw BD. Here's BD. AC should have gone through the center there. That's better. Still not connected. There we go. All right. How are the line segments different? Well, they're different because one of those segments goes directly through the center, AC goes through the center, and then the other, BD, does not go through the center. So AC passes through the center, BD does not pass through the center. How are they the same? Well, if you look at their endpoints are on the circle. A is on the circle, C is on the circle, and then B and D are on the circle. So the endpoints are on the circle. So it names these, both of these segments are called chords. So a chord goes from one endpoint to the opposite. And if it's a diameter, AC is a diameter, then it passes directly through the center of the circle. So why isn't BD a diameter? Because it does not pass through the center of the circle. How does the length of the diameter of a circle relate to the length of the radius? So again, the radius goes from the center to a point on the circle. However, the diameter goes from one endpoint on the circle to the opposite endpoint. So it goes all the way across. So how many radii make up a diameter? 2, right? So the diameter is equal to 2 times the radius. So whatever the length of the radius is, if you double it, you get the diameter all the way across. For the second part of the warm-up, in this first box, we're going to name the parts of the circle as either radius, diameter, or chord. So if I look at segment JK, K is the center of the circle, and J is a point on the circle. So if it goes from center to a point on the circle, that would be radius. JI passes through the center of the circle, which is point K, and J and I are endpoints of the circle, so that would be diameter. H and I are on the circle, however they do not pass through the center, so that would be chord. K is the center of the circle, and I is a point on the circle, so if it goes from center to a point on the circle, that would be radius. JL. So J and L have endpoints on the circle, however they do not pass through the center, so that would be chord. And then lastly, for these last two parts, you're going to find the area of the circle, and the formula for area of a circle is pi r squared, where r is the radius of the circle, and then pi is an irrational number that goes on forever, but for this we're going to be estimating it as 3.14. So we're going to use 3.14 for pi. So the area is how much space it takes up. So in this picture, the area formula is pi r squared, and we're just going to plug in from the picture. So again, for pi, we're going to use 3.14. And then the radius has to go from the center to the point on the circle. So that would be the 12. So to type this in, exponents come first. 12 times 12, or 12 squared, is 144. So I'm multiplying 3.14 times 144, and we'll round to the nearest tenth. So when you type that into a calculator, the area would be 452.2. The units are meters, and because you're squaring the radius, it would be 12 meters times 12 meters. So whenever you have area, your units are always squared. So it's 454.2 meters squared. The formula for circumference. Circumference means around the circle, as if you had a circle here, you could take a piece of string and measure the distance all the way around. So circumference really has two formulas that you can use. The circumference is the diameter times pi. So D is diameter. Or the diameter, if you remember, to get all the way across, you just double the radius. So it's written as 2 pi r, or in other words, if you double the radius, right? If you multiply 2 times the radius, it's the same thing as diameter. So it just depends on what the picture gives you. If it gives you the radius, use 2 pi r. If it gives you the diameter, use diameter times pi. So for this last part, we're finding the circumference. And if I look at the picture, 10.2 is all the way across, so I'm going to use diameter times pi. So if I plug in for my picture, diameter is 10.2, and then pi is 3.14. So if I type this in to the nearest tenth, 10.2 times 3.14, you're going to get approximately, I should have curved these parentheses because we estimated here. We rounded, not estimated, rounded to the nearest tenth. So the circumference is approximately 32, and the units is meters. It's not squared because you didn't plug in 10.2 times 10.2, it was just 10.2 meters. So from the warm-up, this next part is just organizing our key terms that we learned. The first is what a circle is. Your definition is right there, a set of points equidistant from a given point called the center. So I'm going to draw the center here. I'm going to put point C. So to name it, you write circle, and then you use the letter of the center, so circle C. The next thing we learned was what a radius is. So again, the radius goes from the center to a point on the circle. So I'm going to keep the same letter, C, and then a point on the circle. I'm just going to call this B. So CB would be the radius. Then we learned what a chord is, and that is a segment with endpoints on the circle. It doesn't have to pass through the center. So if this is the center here, I'm going to put a point here and a point here. Let's just call this AB. So this would be a chord. And then a specific type of chord that goes through the center is called the diameter. So if this is the center C, it has to pass through there. So I'm going to call this X and then Y. This would be my diameter. And if you remember, the diameter is always 2 times the radius. So for this next set of definitions, we're going to be looking at an angle created in a circle, and then what an arc is, which is technically highlighting a portion of the circumference. So a central angle. First of all, a central angle has its vertex at the center. So vertex at the center. So I'm going to draw the center here. I'll name that B. And it's an angle created is also 60 degrees. So I can highlight the intercepted arc. So from A to C, this is the intercepted arc. That arc is also 60 degrees. In fact, the total measurement all the way around the circle is 360 degrees. So that's just a portion of the entire circumference. So a minor arc is an arc that is less than 180 degrees, which is half a circle, and you use 2 letters to name that arc. So here's an example of a minor arc. So 2 letters or 2 points. I'm going to call this point A and point B. So I'm going to highlight this. Here's my minor arc from A to B. I'm going to say that that is 70 degrees. So what is the notation to say that arc AB is 70 degrees? You would say the measure, so the lowercase m. You're going to draw an arc and record your 2 letters. So the measure of arc AB is equal to, I almost wrote 70 degrees. So if a minor arc is less than 180, a major arc is larger than 180. So to differentiate, they use 3 letters in order to name a major arc. So I'm going to call this X. I'll call this Y. And I'll call that Z. So if I highlight my major arc here, here's my major arc. So I'll say that that is 200 degrees. So to write that out, the measure of arc XYZ is equal to 200 degrees. A semicircle is exactly 180 degrees. And you do use 3 letters for that. So I'm gonna get halfway across the circle. I'm just gonna call this QRS. So there's my semicircle, exactly 180. So the measure of arc QRS is 180 degrees. There's my semicircle. For these next 4 examples, we're going to highlight the arc that's given, and we're going to name these as either a major or a minor arc according to how many letters is given. So for this first example, arc BCA, because it has 3 letters, I know it's major. And because it's major, I know that we're going to be highlighting more than halfway across, more than 180. So if I read the 3 letters, it says BCA. So the first letter is B, so that's where you start. And there's really 2 ways that you can turn from here. You could go clockwise or counterclockwise, but there's only one option in order to trace BCA. So when you start at B, you have to pass through C next because it's the middle letter, and you have to land at A. If you try to go this way, you would pass through A first, but you have to pass through C first after starting at B. So you start at B, you pass through C. It doesn't matter what letters you pass by as you continue on, but you have to end up at A. So you start at B, pass through C, and end up at A. And notice we highlighted something larger than halfway across, or 180 degrees. The next arc has 2 letters, so that would be minor. That means it's less than 180. So we're starting at N right here, and we have to get to J next. And again, there's 2 routes. You can travel this way. However, if I travel this way and connect all the way to J, that would be more than 180, because 180 is from N to K. So I cannot travel that way. So to connect from N to J so that it's minor would be here. The next arc has 3 letters, R, T, Q. So that would be major, more than 180. So I start at R, I have to pass through T next and end up at Q. So the only route to start at R, pass through T next, and end up at Q would be almost all the way around the circle. Lastly, TS, 2 letters, that would be minor, less than 180. Start at T and then connect to S. Obviously, if I go this route, that would be almost the entire circle, and it has to be less than 180, so this would be my highlighted arc. For the next example, we're going to be finding some measurements of the circle. We're going to be finding an angle in the circle, and then the last 4 ask for the measure of the arcs. So a couple things to remember. You might see vertical angles. So this 140 degrees right here, that's vertical to this angle here, which is 104. And don't forget, the intercepted arc is exactly the same as the central angle. A central angle has the vertex at the center of the circle. And then always look for half circles whenever you can find a diameter, like here's the diameter, and you trace the arc here. That's a semicircle, it's exactly 180 degrees. So that means these 3 arcs, this arc here, and this arc here, they add to 180 because it's a half circle. So if I look at number 1, a couple things I notice right away. 87 degrees, this angle right here, that's the exact same degrees as the intercepted arc, TU. So I can label 87 degrees. I also notice that SW is 72. And although you don't have to write the 72 degrees for the angle, I know that if I translate that over here, that would mean that UV is also 72 degrees. So we found vertical angles, and therefore we were able to label the arcs that were identical. So before I fill out all of my measurements here, I'm just going to label everything in the picture. I'm going to find the other 2 missing arcs. So how could I find ST, and then how could I find WV? Well, I'm going to look for half circles. So I'm going to highlight a half circle here. So here's 180 degrees. So all 3 of these arcs should add up to 180. So I already know the 72 and the 87. And then I'm missing this last piece, the ST. So all I need to do is take 87 and add 72 to that to see how much I have so far, which is 159. So then to find ST, I just take 180 minus 159 because all 3 have to add up to 180, and that would give me the 21 degrees. So this remaining arc is 21 degrees. And then lastly, the final missing arc, there's really 2 ways you could do this. I know that all 5 arcs add up to 360 because it's a circle. However, I can highlight this half circle. So these 2 arcs here, I'm just highlighting there, they add up to 180. So if I already know one of the arcs is 72, then I could find the other arc by taking 180 and subtracting 72 from that, and that would give me 108 degrees. I'm sorry. Yeah, 108. Let me fill this out then. 108. All right. So now that we have all of our arcs in this picture, let's go ahead and start filling in our information. So the measure of angle UXV, that is the central angle. If I trace UXV, that would be this angle here, which is 72 degrees. And then the next four are arcs. So since the next three arcs have two letters, my answer should be less than 180. So if I trace ST, ST is from here to here. So that would be 21 degrees. WV. So WV is from here to here. That would be 108 degrees. TW, I'm going to use a different color to trace TW. So again, it has to be less than 180. So from T to W, how many arcs make up TW? 2 arcs. Well, to get the total, I just have to add 72 plus 21, and that would give me 93. Lastly, TVW. Let's highlight that first. So I have to start at T. I have to pass through V and end up at W. Starting at T, passing through V, and ending up at W. So how many arcs make up this green highlight? 3 different arcs. The 87, the 72, and the 108. So all I have to do is add 87 plus 72 plus 108, and I would get 267 degrees. For example 2, we're asked to create an equation from this picture and solve for x. So what I noticed so far in this picture is that our S has an expression to represent the arc. It's 15x minus 26, and then ST is 26 degrees. And if I connect both of those arcs together, they make 180 degrees. So that's an equation I can use in order to find x. 15x minus 26 plus the 26, those together make a half circle, which is 180 degrees. So that is one route I can use in order to solve for x. So my constants here cancel out, negative 26, positive 26, so I'm left with 15x equals 180. And then the last step is to divide both sides by 15, and I get x is equal to 12. A second route you could have created in order to find the missing variable is to figure out what just this arc is equal to. And you could have done that by taking 180 and subtracting 26 from that, which would give you 154 degrees. So you could set 15x minus 26 equal to 154, and then you would get the exact same answer. You get x is 12. The last set of these notes is looking at what an inscribed angle is. So taking a look at this picture, you can actually manipulate the angles by scanning this and using GeoGebra to investigate the connection between the central angle and the inscribed angle. However, this picture shows an example. So where's the central angle? I know if it's a central angle, the vertex is at the center. So the center is A. So I know the central angle is angle BAC, this angle right here. Or you could name it CAB as long as A is in the middle. And the reason I know that is because the vertex is at the center of the circle. All right, what is the measure of arc BC? Well, I know that it has 2 letters, so it better be less than 180. And if I look at my picture, the central angle, which is 120, is exactly the same degrees as the intercepted arc. So that is also 120 degrees. This third part is naming a different angle, angle BDC. So I'm going to trace that. So where is BDC? So BDC, in other words, the 60-degree angle here, that is inscribed. It definitely has a different location than the central angle. So it's asking, how is that measurement, which is 60 degrees, so this inscribed angle is 60 degrees, how is that related to the central? If the central is 120 and the inscribed is 60, it's exactly half the size or half the value. If you take 120 and divide by 2, you get 60. And if you use the animation, you would notice that this was always true no matter how you manipulated this picture. The inscribed angle is always half the central. You could think of it like when you pull back that vertex, it gets smaller. All right, so where's the position of the inscribed angle's vertex? If I look at the vertex is D. The vertex is no longer at the center, it's on the circle. So on the circle. So let's formally record our observation of an inscribed angle. If it's inscribed, the vertex is on the circle. So I'm going to draw the vertex right here. I'll name that D. So an angle needs 2 more points here. So I'll call this B and I'll call this C. So here is my inscribed angle. So what is the observation of the inscribed angle, which I'll use the same degrees as the picture previously, and the intercepted arc? So if you remember, this is the intercepted arc right here. We said that the intercepted arc was always double the size. So we would have to double 60 to get 120, or if you say it in reverse, the angle is always half the size of the intercepted arc. So let's fill in the observation. There's 2 ways you could say this. The inscribed angle, the 60 degrees, that's always half the arc. Or you could say the arc, which is 120, is always double the inscribed angle. Which of these is easiest to use? I'm going to use the one without the fraction. So I'm going to say the arc is always double the angle. And that's the equation I'm going to set up for the next example. So for these last 2 examples, we're going to use the observation of an inscribed angle in relation to the intercepted arc. And here is our equation. So the arc, which I'm going to highlight in yellow, is always double the angle, which I'll highlight in pink. So in this first picture, the arc is 62 degrees, and the inscribed angle, this angle right here, is what we're trying to find. We're trying to find WXY. So I'm going to write that equation. The arc is always 2 times the angle. So in this picture, the arc is 62 degrees, right? And that's always double the angle, which we're trying to find. So I'll just call that X. So in order to solve for X, divide by 2. So the angle should be 31 degrees, right? It's always half the size. You don't have to write this equation. Technically, I agree. You could probably do this in your head. Just cut 62 in half. All right, for this last one, let's highlight the intercepted arc right here. So that measurement should always be double the angle, the inscribed angle, which is 113 degrees. So we're trying to find DGF, which our answer should be bigger than 180 because it has 3 letters. So again, you could do this without work if you understand the relationship, but if you want to use the equation, you could say the arc is always double the angle. So in this picture, we're trying to find the arc, right? Which is X, and then the angle is 113 degrees. So if you double 113 degrees, the arc would be 226 degrees.